Hello everyone, welcome back to Spectrum Classes. In this video, we are going to discuss the equilibrium coefficient of iodine in water and n-hexane system. We are going to perform the lab activity, but before that, we are going to discuss about the concept of this equilibrium coefficient and how it is different from the distribution coefficient. So let's start with the video. So before moving to the equilibrium coefficient, we are first discuss about the partition coefficient in brief. So here I have shown you this picture. This experiment I have performed in my previous lab activity, in which we have determined the equilibrium, in which we have determined the partition coefficient or distribution coefficient. It is represented by Kd. So here we are having water plus n-hexane system. In n-hexane we have different concentration of iodine, and once the equilibrium is established between this n-hexane and water system like this, here the concentration of iodine is different in both the layers since it is more soluble in organic layer. So here we are just going to see the distribution coefficient for iodine in these two solutions. So here for this I have written over here. Here we are having this system first, which we performed in the previous experiment, and for this we are having Kd. But in water system, this iodine can also distribute itself like I2 plus I minus, which forms a complex I3 minus. And for this reaction, we are having this equilibrium constant. So here there are two different things. One is distribution coefficient and the other one is equilibrium constant. I hope you understand in this manner. Now some of the student will ask, if we are having this I2 distribution coefficient, then how it forms? So for this purpose I am just going to show you in the next slide. So here this distribution coefficient, how we are going to mention this iodine in n-hexane and this iodine in water. This is the distribution coefficient. If suppose we consider this I2 hexane as C1, because it is easy to write down in a notebook, then we can write down this formula in this manner. Fine. So I2 in water will be equal to C1 upon Kd. C1 is I2 in n-hexane. Now coming to the point that how this reaction will come. I2 plus I minus will gives you I3 minus, right? So here in this case we have taken only water. But here in this case we have taken different concentrations of Ki as well as different concentration of iodine. That is why we are having an equilibrium in the aqueous layer, which gives the equation I2 plus I minus, which comes from this Ki, and that forms I3 minus complex. Here you can clearly see organic layer and aqueous layer is different from the previous case. Here only iodine is distributed itself, but here it forms a complex and more iodine is going into the aqueous layer. So here what we are going to see, I2 plus I minus will gives us I3 minus, and for that reaction we are going to determine the equilibrium constant. Right? I hope you understand with this clearly. So for equilibrium constant, product concentration divided by reactant concentration. Now the important point is that how we are going to determine this I3 minus, this I2 and this I minus. So this I2 is simple and okay. In the previous case we have determined this. So I2 water we can determine by knowing this distribution coefficient and the concentration in organic layer. In that way we can determine this I2. Now the question comes, if we can determine this I2 in n-hexane directly, then why not this iodine in water directly as we did in previous case, right? Because in this case we are having iodine in the form of I3 minus also. in this form also, iodine which is available over there. So some form complex and some is in free state. So it distributes itself in two different forms, I3 minus and I2. That is why we cannot directly consider the concentration of iodine in water layer. So what this has I2 plus I3 minus, which is determined by direct titration, and we have also determined the I minus concentration. So for that we are following few steps. So this K can be written like this as we discussed in previous slide, and now the total concentration of iodine in water layer can be considered as I2 water plus I3 minus water, as I explained in previous slide. Here we can replace this I2 from the distribution coefficient C1 upon Kd. So by knowing that, and this C2 we determine from direct titration. So C2 is determined direct titration. I2 we can replace from there. So we can directly have this I3 minus water here in this manner. Fine. Now the second point is how we are going to determine the I minus and I3 minus in water. So suppose we are considering the initial concentration of potassium iodide in the aqueous layer, which is we can written in the form of C3. This will be equal to this much, right? I minus, here you can see I minus and I3 minus. This is from Ki. So initial concentration is C3 and I3, this C3 will be equal to I minus and I3 minus, because this I minus will associate with this iodine and form I3 minus. So in this manner it consists or comprises of these two species. Now how we are going to determine this? So C3 is known to us because we already added the known concentration of potassium iodide solution. I3 minus we determined in previous case. Now we can directly determine this I minus. So here this I minus is equal to C3 minus this I3 minus. So I3 minus is what? C2 minus C1 upon Kd. Now here I have summarized these two formula. This is for partition coefficient and this is for equilibrium constant, and all these concentrations are replaced by their C1 C2 forms, right, and Kd. So now the main aim is to determine all these terms. C3 is known to us, Kd is known to us from the previous experiment. Now the main aim is we are going to titrate and determine the C1 and C2. Fine. So here we are going to perform the lab activity, and for that purpose we require this many solutions. The same solutions as we required in previous case, only the difference is we do require different concentrations of iodine, m by 10, m by 15 and m by 20. For this we are going to use the same formula, and this formula molecular weight, molarity into volume upon 1000. And to dilute from one to another, we use this normality or molarity equation. N1V1 is equal to N2V2. If molarity and normality is same, then we can apply this. Now we are going to perform the lab activity. So here we are going to see the lab activity, and for this we are having these many solutions, right? So here m by 10 Ki, m by 15 Ki, m by 20 Ki solutions are required, and these solutions plus starch, which is freshly prepared, and saturated solution of n-hexane, still water. And to prepare 3 sets we are having this 3 reagent bottles, and in this, to vary the concentration of iodine, we are having this 20 ml, 15 ml and 10 ml of n-hexane solution. And in the second set, just to vary the concentration, we are going to add 10 ml of n-hexane. Here I am just going to add 10 ml of n-hexane in the third set, because 10 plus 10 is iodine solution plus blank n-hexane just to vary the concentration of iodine. In the second set, we are going to add 5 ml of n-hexane plus 15 ml of iodine. And now we are going to add 20 ml, 15 ml and 10 ml respectively saturated solution of iodine in these three bottles. Here it is 15 ml and now 10 ml in the third set. So each bottle contains 20 ml of organic layer in this manner. To this we are going to add m by 10 potassium iodide in the first set, 100 ml. In the second set we are going to add m by 15 potassium iodide solution. In the previous experiment we have added only water, 100 ml of water, and here in the third set we are going to add m by 20 potassium iodide solution. So this is for calculation of equilibrium constant. For distribution coefficient calculation we have added just water only, 100 ml of water. And here we shake these bottles repeatedly after each 5 minutes for 1 hour. And here you can clearly see the difference in the organic layer. In the previous case, organic layer is dark and aqueous layer is light in color. But here in this case, you can see the visible change in the previous and the second experiment. So organic layer is the upper part, and now after 1 hour we are just going to separate these aqueous and organic layers. So here we are going to transfer into the separating funnel just to separate these two layers. When you are using this separating funnel, so you just revert it to separate the organic layer and vent off the pressure. Now remove the stopper and separate the organic and aqueous layer in separate reagent bottles. So we are here collecting the organic aqueous layer, and then we are going to collect the organic layer. At this moment you be careful and now discard this layer and now collect again this organic layer. So here in this manner we have separated organic and aqueous layer for all three sets. Now we are going to titrate with the help of this m by 10 sodium thiosulfate solution. Preparation is given in the previous experiment. We rinse the burette with this and now fill. So while you are filling this, you just have some extra volume. This nozzle. Now adjust it to 0. Take 50 ml of this into the conical flask and do the titration. When this color is little faded, then add the starch indicator to this. Initially we are not adding the starch indicator because it forms strong complex which may vary the end point. Here is the end point. Now see the readings. 0.567. Now we are going to titrate organic layer with the help of m by 100 sodium thiosulfate solution. So we are going to take 10 ml of this organic layer in the conical flask and we are going to titrate it with m by 100 sodium thiosulfate solution. Now we are going to add starch and here at the end point there is no color. Now similarly we are going to see the readings of the burette and that will be used for calculation. So we have seen the lab activity and from there we are going to do the calculation part. For calculation part we are going to use this formula, and as I mentioned earlier that for 1 mole of iodine 2 mole of sodium thiosulfate is consumed, and here A1 and A2 represents the number of gained electrons per formula unit of iodine in the balanced half cell equation, and similarly number of A2 is the number of loss of electrons per formula unit in the balanced equation of half cell reaction. And from the lab activity we have seen m by 10 sodium thiosulfate is taken for aqueous layer in this case. So here this is the volume consumed of sodium thiosulfate and this is titrated against m by 10 and this is titrated against m by 100 in this case. Fine. So the concentration is this. So here in this formula we are going to put m by 10 for aqueous layer. This is our V1. This is our V2. This is our M2 is equal to this. So we can calculate the M1. Fine. And for sodium thiosulfate, if you are putting this side sodium thiosulfate, then use A1, A2 accordingly. I have mentioned over there. And from there we have calculated the M1. M1 is this much. Fine, for all three. Similarly, we have taken 10 ml of organic layer and for that we have titrated. This is the initial reading, this is the final reading of the burette, and on subtraction we are getting this. On putting these values in the formula, so what we will get? We will get 10 into m by 10 is equal to 2 into 10 into m1 here in this case again. And from there we are going to calculate. So this is the concentration of iodine in organic layer. If I divide this C1 upon KD, KD is, here I have written, and KD is this much. Here is the KD, distribution coefficient. So C1, which I have determined from here, this is the C1 and this is divided by KD. KD is from here. Fine, so we get this much. So in this manner we are able to consider the concentration of iodine in aqueous layer. Fine. And now further we are going to calculate. So I have taken this C2 from previous slide, C1 from previous slide, C1 upon KD from previous slide. Now I'm going to subtract this C2 minus C1 upon Kd. So this is how we are going to get this I minus. I3 minus, fine. So here we are going to get this I3 minus. Now C3 is known to us, the concentration of Ki, fine. And we are going to subtract from this C3, this to this we are going to subtract, and we get this much of value here in this case. And this is the concentration of I minus only. Now putting all these in the formula of K. K is equal to I3 minus upon I2 upon I minus. These all are concentration terms. So I3 minus is what? This. This is in the numerator. I2 minus is what? This is I2. So this is in the denominator. Here you can see. And here is I minus. And this I minus is this whole term. So on putting all these values in this formula, we are going to have this equilibrium constant different, which is quite different. So I would suggest this is only for the practical purpose, not for the research purpose. If you are doing the research, do take 3 concordant readings for each set. Only then you can have precise values, right? So here we are having this, on taking the average, we are going to have this much of equilibrium constant. Fine. I hope you find this video helpful. If you find this video helpful, please like, share and subscribe. Thank you all. Thanks for watching.